So, good morning class. Today we will further discuss about stoichiometric defect. So, in the last session we discussed the entire flow chart of different types of defects or imperfections found in solids. So, we discussed one type of stoichiometric defect, that is vacancy defect. So, we have to discuss three more types of stoichiometric defect, that are interstitial defect, shocky defect and Frenkel defect. So, we are discussing stoichiometric defect. So, we are discussing stoichiometric defect, stoichiometric defect in solids. So, we have already discussed that stoichiometric defect is of four types. These stoichiometric defects are of four types: vacancy defect, interstitial defect, vacancy defect, interstitial defect, shocky defect and Frenkel defect. Vacancy defect, interstitial defect, shocky defect and Frenkel defect. So, we have already discussed this type of defect, that is vacancy defect. We have to discuss interstitial defect, shocky defect and Frenkel defect. So, these three defects we have to discuss. So, let us discuss one by one. So, let us discuss the second type of stoichiometric defect, that is interstitial defect, that is interstitial defect, interstitial defect. So, what happens in interstitial defect? So, in case of interstitial defect, let this be our crystal system, or let this be our three-dimensional crystal, which and let these be lattice sites and let these be the lattice sites. And the particles are occupying their lattice positions. So, what happens? Some of the particles from outside, they occupy interstitial positions. So, this is the regular interstitial site, regular lattice site, and these black circles are representing particles occupying interstitial position, particles occupying interstitial position. So, what happens in this type of defect? The particles are found in their lattice sites, comma, but some of the particles from outside occupy interstitial position, they occupy interstitial position. The second point about this type of defect is, they are due to this effect, the density of the crystal or solid, the density of the solid increases. Due to this defect, the density of the solid increases. And the third point is, this type of defect is found in non-ionic solids. It is found in non-ionic solids. So, this is the type of stoichiometric defect. So, the first type of stoichiometric defect, that is vacancy defect, we have already discussed. So, we are discussing the different types of stoichiometric defect. In this category, the second type of stoichiometric defect is interstitial defect. So, what happens in this type of interstitial defect? The particles are found in their regular lattice positions or lattice side, but some of the particles from outside, they acquire the interstitial positions. Interstitial position means the positions between the regular particle lattice positions, and so the particles are found in their regular lattice side, but some of the particles from outside, they come and they occupy the interstitial positions. So, these are the particles occupying interstitial positions. Because the volume is same, but the number of particles are increasing, and since density is equal to mass upon volume, volume is constant, it means that if mass is increasing, this means the density of the crystal will also increase. And the third point is this type of defect is also found in non-ionic solids. Now let us discuss about the third type of stoichiometric defect, that is Schottky defect. The third type of stoichiometric defect, that is Schottky defect. Schottky defect. Now, what happens in this case of Schottky defect? The first point related to this is it is always found in ionic compounds or ionic solids. The second point about this is it is equivalent or analogous to vacancy defect. It is same or equivalent to vacancy defect. So, let us define a case of ionic compound consisting of two cations, a cation A plus and an anion B minus. So, let this be the arrangement of ions in the compound AB. So, these are the arrangement of ions in the compound, in this ionic compound, and these ions are linked by electrostatic force of attraction, which is represented by this dotted line, broken line. So, these are the electrostatic force of attraction which exist between these ions. So, this dotted lines represent electrostatic force of attraction, so here it will be B minus . So, what will happen in this case? Let here it should be A plus, but this is vacant. So, here it was supposed to have a cation A plus, but this site is vacant. Similarly, to maintain the neutrality of the crystal, the anion will also miss from some other lattice position. So, here it was supposed to have a cation A plus, but it is not having, it is having a vacancy defect, and here it was supposed to have B minus anion, but it is not found, it is having vacancy defect here also. So, what happens in this type of crystal? Equal number of cations and anions are missing from their lattice sites. So, they are missing, equal number of cation and anion are missing from their lattice sites. So, to maintain electrical neutrality of the crystal, to maintain the electrical neutrality of the crystal. So, since cations are and anions are missing in equal numbers, that means that cations and anions are making a pair, and these pair which are being missing or which are moved from their sites leading to the formation of vacancy defect. So, these are called Schottky pairs. These are called Schottky pairs. These equal number of cations and anions, because we have already seen that in case of Schottky defect, equal number of cations and anions are missing from their lattice positions. So, since if one cation is missing, then one anion will also miss. If two cations are missing, then two anions will also be missing, and if three cations are missing, then three anions will also be missing. So, since there is equal missing of cations and anions, so we say that cations and anions are occurring in a pair, and these pair of cations and anions which are missing from their lattice sites, it is called Schottky pairs. So, one cation and one anion, they make a Schottky pair, and there will be a certain number of Schottky pair which will be missing from the lattice sites of this ionic compound. So, here it was supposed to have a A plus cation, and here it was supposed to have a B minus anion. Next point, it is found in those ionic compounds in which coordination number is high. It is found in those ionic compounds in which coordination number is high, it is more. Next point, it is found in those ionic compounds in which size of cation is nearby equal to size of anion. That means, the size of cation should not differ much from the size of anion. For example, let us see some of the examples of these compounds like NaCl, KCl, KBr and AgBr. And AgBr is a compound, it is a compound which have both the defects, that is Schottky defect and as well as Frenkel defect. So, this is the vacancy created due to missing A plus cation, and here vacancy defect due to missing B minus. So, this was all about Schottky defect. First point, it is found between ionic compound and it is analogous to same as that of vacancy defect. So, let us consider an ionic compound made of cation A plus and anion B minus. So, this is the network of cations and anions which is existing in that compound in that ionic compound. So, in this case of Stoichiometric defect, equal number of cation and anion are missing from their regular lattice site, leading to the formation of vacancy defect. So, what happens in this Stoichiometric defect? Equal number of cations and anions are missing from their lattice positions, from their lattice sites, and this is totally for the maintenance of electrical neutrality of the given ionic compound. And this equal number of cations and anions which are missing from the lattice position, from the lattice sites, they contribute a set, a pair, and this pair is called Stoichiometric pair. This Stoichiometric defect is found in those ionic compounds in which coordination number is high, and those ionic compounds in which size of cation is nearby equal to size of anion. For example, NaCl crystal, KCl crystal, KBr, AgBr, and AgBr is a compound in which both of the defects are found, that is Stoichiometric defect also and Frenkel defect also. Now let us see the fourth type of stoichiometric defect, that is Frenkel defect. Now let us come to the fourth and the last type of stoichiometric defect, that is Frenkel defect. Frenkel defect. So, this Frenkel defect is also found in ionic compounds. It is also found in ionic compounds. So, let us see what happens in this case. And the second point, it is analogous to interstitial defect. It is analogous to interstitial defect. So, what happens? Let us see. So, let us again consider a crystal, a ionic crystal made up of cations A plus and anion B minus, A plus, B minus, B minus, A plus, B minus, A plus, A plus, B minus, A plus, B minus. So, this is the ionic compound made up of cation A plus and anion B minus, and again they are linked by electrostatic force of attraction, which is shown by dotted lines. So, this is the ionic compound made up of cation A plus and B minus. So, what happens in this case? The cation moves from its normal lattice site and occupies a interstitial site. So, what happens in this case? Cation moves from its lattice site and occupies interstitial site So, this was supposed to be the lattice site of A, lattice site of cation A plus, and this cation plus A plus has moved from its lattice site and it is occupying interstitial or A plus cation A plus cation occupying interstitial site, A plus cation occupying interstitial site. So, cation moves from its lattice site and occupies interstitial site. So, due to this defect, there is no change in density and electrical neutrality. The compounds remain still electrically neutral. There is no change in density of the crystal and electrically it is still neutral. Third point, it is found in those ionic compounds in which coordination number is low. Coordination number is low. Fourth point, it is found in those ionic compounds in which size of anion is greater than size of cation. For example, AgI, AgCl, AgBr, mainly halides of silver, etc. So, this was all about stoichiometric defect consisting of 4 types: vacancy defect, interstitial defect, Schottky defect and Frenkel defect. So, we have already discussed the 3 types of stoichiometric defects, that is vacancy defect, interstitial defect and Schottky defect. So, this was the 4 type of stoichiometric defect found in ionic compounds. This is analogous to or identical to interstitial defect. So, let us consider a crystal made up of ions, that is cation A plus and anion B minus. So, what happens in this case? This was supposed to be the normal lattice site of cation A plus. So, in this, due to this defect, the cation A plus moves from its normal lattice site and occupies the interstitial site. So, the cation moves from its normal lattice site and it occupies interstitial site. There is no change in density and it is still electrically neutral, the crystal is neutral still. The third point is, this kind of defect exists in those ionic compounds in which coordination number is low. The fourth point, for the existence of Frenkel defect, the ionic compound should be such that the size of anion should be greater than size of cation, and mainly this type of defect is found in silver halides like AgI, AgCl and AgBr, and AgCl is AgBr is a compound in which both the types of defects exist, that is Schottky defect and Frenkel defect. Thank you, class.